Okay, we're ready to now talk about common logarithms. There's many times in math where a number is implied, like when we have something like square root of x, we know that this is a number 2. Right here is the index. We also know that sometimes we have a squared b, where this number 1 is invisible, but it's implied that that's b to the first. This happens a lot in math, where there's just an implied number, and the same thing happens with logarithms. If we do not have a number here as the base of the log, it is implied to be 10. And that's why we call it the common logarithm. Now, back in step 19, we were solving exponential equations like this. We would simply rewrite the larger number expressed as the base raised to a common base raised to some power, but you cannot express 19 as a power of 4. You cannot express 19 as a power of 2. It's not possible. And this happens sometimes. So in step 19, all of our problems worked out really nicely. But here we are in step 20, where we need another method to try and solve this exponential equation. And we can use logarithms to accomplish this. And the way we're going to do it, we're going to literally take the log of both sides of the equation. Just like that. Next, we're going to think about that property we learned in our last video that says that if you have an exponent in a logarithm, it can come down front and become a coefficient. We actually did that in reverse in the last video, where we took the coefficients and made them exponents so that we could consolidate our logs, but it does work in reverse. So now we have x log 4 equals log 19. These are both base 10 because I don't have a base written. It's implied that it's base 10. Now you might say, well, why did you move that exponent down? Well, let's think about our goal here. Our goal, anytime you see the word solve, means get the variable by itself. So if I have two sides of an equation here, which I always do, I'm trying to get x by itself. I can't do that when it's taking on the role of an exponent. So I've moved it down front. Now, think about how you would solve something that looked like this. You would divide by 4, right? Well, the same thing is happening here because the log of a number is just a number, and it's just multiplied by x. So to remove the log of 4, we need to divide by the log of 4. But these things are a package deal. You can't just divide by 4. That's not possible. Log 4 it has to stay together. It's a package deal. So on the left side, they cancel out, and I'm left with just x, which was my goal. On the right side, I can type this on the calculator because our calculator can handle common logarithms. It's really helpful. So let me move that down and pull my calculator up. All right, clear out my calculator. Back to the home screen. I can type everything that's on the right into the calculator. I'm going to type log 19 divided by log 4. Notice I closed the parentheses before I divided. I went the log of 19 on the top and the log of 4 on the bottom. It also tells us in our problem round to the nearest 10,000th. That's 4 decimal places for this problem. So my answer ends up being 2.1240 when I round to the nearest 10,000th. All right, let's check that using our calculator. Is 4 to the 2.1240, does that equal 19? Now it's not going to be exact because we've rounded, but let's try it out using our calculator. 4 caret 2.124. Yep, that that would round to 19. So we know we're right. We've got the right answer. You can also use alpha y equals if you'd rather have the fraction and type log 19 on the top and log 4 on the bottom. Notice I'm not closing my parentheses. I could for good measure, but it's going to give me the right answer just because I use the fraction button. It'll still work out. And it actually filled in my parentheses for me. All right, let's take a look at another example. Here we have 2 more. Let's try one together. Let's take the log of both sides. Since I cannot express 15 as some power of 3, I'm going to take the common log of the left and the common log of the right side. I'm going to move this exponent down front to become a coefficient. Then I'll divide both sides by the log of 3. Using my calculator, the log of 15 divided by the log of 3 is 2.4650 when we round it. Notice you cannot cancel out the words log because you need to remember that the log and the 15, the log and the number that comes after it, they're a package deal. So you cannot just cancel out the word log because it's actually a function that's happening with the number. Okay, this brings us to our change of base formula. We can express log base 3 of 20 in terms of common logarithms. This is really helpful because now we'll be able to have the calculator compute this. Up until this point, we haven't been able to do that. The change of base formula simply states that we're going to put the log of the large print number on top and the log of the base on the bottom. And we type it into our calculator to get our answer. The log base 20, the log base 10 of 20 is my numerator, and the log base 10 of 3 gives me 2.7268. That's how we can use our change of base formula with our calculator. The next thing we're going to talk about is what is a natural logarithm. So in math, we have a lot of interesting numbers like pi, 3.14159, and so on, radical 2. There's also a number, and the number is e. It's a script little letter e, and it's an irrational number. Its value is 2.71828. It's considered the natural base, all right? And we use this a lot when we're trying to model continuous exponential growth or continuous exponential decay. It's going to come up a lot. E is just like pi. It's just another number. Instead of writing out that really long number that never ends, we just put E. And if you press E on your calculator, you'll see it's going to be the blue button and then the natural log button. E to the first is just 2.7182 and so on, just like it says in our notes. So E is already saved into your calculator, just like pi is saved into your calculator. Second caret tells you what pi is. These numbers are already stored in our calculator for us to use. And then we use them when we are, like I said, modeling continuous growth, continuous decay. All right, the natural base exponential function, so e to the x, would have an inverse, which is the natural logarithm. A natural logarithm just means it's a log with a base of e. So we just practiced looking at logs with a base of 10 of some number. So when that happens, we don't even have to put the base, we just write it like this. Think of natural logarithms as a shortcut. We could write log base e of x, but that takes 4 letters. Instead, I can just use natural log ln. I know it's kind of backwards, you'd think it would be nl. Natural log of x is the same thing. It's just a logarithm that has this special 2.71 number as its base. Doesn't mean anything different. All right, let's practice going from exponential to logarithmic form again using e. All right, so we want the log base e of 8 equals x. Remember, we just make a continuous circle. However, we don't ever write log base e. We write natural log of 8 equals x. And again, that's something we can type on our calculator if we want to. The natural log of 8 is 2.079. So these are just numbers that we're creating. Logarithms are just numbers. Let's try this next one. Log base e, again, I'm not going to say log base e, I'm going to say natural log of x equals 5. Pause the video and try the next 2 examples. The natural log of 9 equals x, and in 1b, the natural log of x equals 7. Let's go in reverse now. Now we're going to start with a logarithmic equation, and we are going to write it in exponential form. We are saying that we're starting with our base right here, which is e, to this number, 0.7741 equals x. Now, if that gives you trouble, you could do an intermediate step. You could rewrite this as a log base e of x equals 0.7741. That's okay to do. And now you could easily see that we do e to that power equals x. If that helps you to rewrite natural log as log base e so that it looks a little bit more like this Step 20a video, you can do that. One thing I want to point out is that this little squiggly equal sign means approximately. So to be consistent, that implies that some rounding has happened. We should keep it a squiggly bracket. Let's try this next one. Our base is e to the x equals 10. All right, let's use properties of logarithms with natural logarithms to consolidate them and express them as a single logarithm. We're going to do the same thing we did when we had the word log written here as we do when we have natural log. Coefficients can become powers in our logarithms. A lot of times, because writing ln kind of looks like a 1, it's okay if you want to do it in cursive. That sometimes helps you remember that that's the natural logarithm. Now, because I have subtraction, that means I can take these components and divide them and express them with one logarithm. 10 cubed over 8. Now I could clean that up a little bit more because 10 cubed is 1,000 divided by 8. And finally, let's use our calculator. What's 1,000 divided by 8? 125. This is my final answer. That is much simpler than what I started with. However, if I type that on my calculator, you'll see that it's the same thing. Let's check it. 3 times the natural log of 10 minus the natural log of 8 gives me 4.828. The natural log of 125 also gives me the same exact number. So I know that I've successfully condensed these logarithms into one logarithm. Try picking the second one. First, I look for any coefficients that can become exponents. Natural log of 40 plus the natural log of 1/2 squared plus the natural log of x. All of these addition signs mean that I can express this as 1 natural log 40 times 1/2 squared. Remember, 1/2 squared is just 1/4. So if I do 40 times 1/4, I'm going to get 10. So these two multiply gives me 10, and then I multiply it by the x as well, and that's my answer. All right, let's use these properties to solve this exponential equation. Okay, remember, solving just means getting x by itself. If I have to clear everything off of this side of the equation, except for the x, that means I need to get rid of 4, e, -2, -5. We're going to use what we know about solving equations to accomplish this. I'm going to first add 5 to both sides. So now I have 4e to the -2x equals 8. I can also get rid of this coefficient of 4 by dividing by 4. So I have e to the -2x equals 2. Okay, our x that we're trying to solve for is still trapped as an exponent, and the only way that we can bring it down front and make it a coefficient is if we have a logarithm. Now, rather than take the log of both sides, I'm going to take the natural log because I'm using e as my base. So if I take the natural log of both sides here, try to squeeze that in a little bit better. There we go. Now this exponent can come down and become a coefficient. -2x, natural log of e, equals the natural log of 2. One fun fact I'd like to point out though, use your calculator, type in the natural log of e. And again, that's e to the first because there is no exponent. What do you get? You get 1. Anytime you have the natural log of e, it's just going to equal 1. So it cancels out. And now we have -2x equals the natural log of 2. We're in the home stretch. Here's our variable. We're trying to get it by itself. All we have left to do is to divide by -2 on both sides. What you do to one side, you do to the other. Even up on this step a few steps ago, we needed a natural log on the left so this exponent could jump over the natural log. So we had to give the right side a natural log. We couldn't just do it to one side and not the other. So now I end up with x is approximately, using our calculator, the natural log of 2 divided by -2, which is approximately to the nearest 10,000, -0.3466. The very last last thing we're going to talk about in this video, and I know this has been a longer video, is an example where we can use this common logarithm and this common base of e. In savings accounts, in banks, interest is compounded continuously very often. And there's a master equation that's pretty easy to remember, actually. And it's A equals PE to the RT. Some people call it the A-PERT equation. Here, we can take all the information we're given and plug it into this equation to get our answer. A few things to point out. A is the amount that we end with. P is the principal. It's what we start with. R is the rate, and T is the time. So if we start with this equation, A equals P E to the RT, let's take each little bit of information that we're given and plug it in. Her grandparents deposited $3,000. That's what they started with, $3,000. E is always going to be E. It's not a variable, it's actually representing a number. Paying 4% interest. As a decimal, that would be 0.04. Compounded continuously, that's where we get the E from. Assuming there are no deposits or withdrawals from the account, what will be the balance after 10 years? So we'll put a 10 in for T. And solve. At this point, we just use our calculator to come up with our answer. We're typing 3,000 E, and then we're typing 0.04 times 10. And that means that after 10 years, our balance is going to be $4,475.47. We rounded 2 decimal places because we're dealing with money. But sometimes they don't ask that. Sometimes they say, how long will it take for the balance to reach? That means, when will it end up being $10,000? So maybe Angelina was really excited on her 10th birthday that she already had $4,400. But she says to her grandma and grandpa, well, when do you think it'll grow to be 10,000? So we put 10,000 in our final amount. We know we started with 3,000. We know it's compounded continuously, so we say E as 0.04 for our rate, but we don't know the time. So now when you think about solving this, it's going to be a little bit more challenging because our variable is our exponent, and it's not isolated yet. So the first thing we need to do is divide by 3,000 on both sides. So here I have 10 over 3, so it would reduce, equals E to the 0.04t. Again, I need to get this t out of the exponent. And the only way to do that is if I take the natural log of both sides, so my exponent has a natural log to jump over. Natural log of 10/3 on the left equals 0.04t. That's my entire exponent. Natural log of e. But remember, the natural log of e is just 1, so it cancels out. And the only thing I have left to do is divide by 0.04. This is what I have to type into my calculator. Typing in the natural log of 10/3 divided by 0.04. And I get approximately 30 years for my final answer.